In this lecture, we'll see the relevance of heat transfer to engineering applications in general and to specifically chemical engineering applications. So before we go into the relevance, let us first define what heat is. Many of us have an intuitive understanding, but just to be more quantitative, let us define heat. So consider a system in which this boundary marked by red is the system, and there is some fluid that is entering the system at some temperature and exiting the system at some other temperature. So we are talking about heat transfer in and out of the system, and we want to understand what we mean by heat. So let us look at the overall energy transfer, a kind of an overall energy balance. So we have two kinds of energies here, the macroscopic and the microscopic or the internal. The macroscopic energy is also called as a mechanical energy. It has got three important terms. The first coming from the kinetic energy of the bulk motion. So here U1 is the velocity, mean velocity of this fluid flowing through this pipe. Then you have the potential energy, and this is called as a flow work, which you might have studied in transport phenomena in the previous semesters as well as in thermodynamics. So these three terms forms the mechanical energy. Then we have thermal energy. So consider a small packet of fluid, and if you zoom in to the molecular level, we'll see that the molecules are actually moving in a random fashion, but the whole packet itself has a velocity u, which is in this direction. So the mean velocity of all these random velocities is u, but each of them have a randomized thermal energy. So this thermal motion or the random motion is associated with what is known as the thermal or the sensible energy, denoted by kT. And the conventional sense, it is just the temperature that we know it as. So kT has the units of energy, whereas the temperature could have different units depending on the system that we use. So we have this internal energy, the thermal energy, which is related to the random motion of molecules. It could be random translational, random rotational, or vibrational. There is also another component of a thermal energy, which is called as the latent heat. Latent heat comes from interaction between molecules. So when you have a phase change, that is from solid to liquid to gas, the phase change happens because of presence of this intermolecular interactions. And other than that, we have other forms of energy which we lump together for the purpose of heat transfer and call it as other internal energy, which could be energy stored in chemical bonds, which is intramolecular, and the nuclear energy. So what we mean by heat is this entire term, that is the macroscopic mechanical, microscopic thermal. Other energies are not taken as part of heat for the purpose of heat transfer problems. Now, having defined, understood what heat is, let us look at its relevance. So this is an energy flow diagram of where energy source is, how we transform energy, basically consume energy, and how it is converted to waste heat. So if you see, this is the statistics of US. Most of the energy source that we have are chemical form, that is petroleum, natural gas, coal, Energy is stored in a chemical form, which is converted to heat, and then we use it for different applications such as electricity generation, transportation, industrial, and so on. The pattern for India is slightly different. We use nearly 40 to 50% of our energy consumption comes from coal. Right. Now, the important thing to note here is this is the uh, consumption. And in this consumption, this is the waste and this is the useful power. We see that the waste energy is nearly 60%. So the relevance of heat transfer is with respect to this entire picture that we have shown here. So, what are the challenges in energy and heat transfer? The main thing is to reduce waste energy by increasing the efficiency, because most operations are very efficient in high temperatures. You also need to design very good conductors or insulators or fluid heat exchangers and radiation surfaces. So the challenge of energy consumption, energy generation consumption, all amounts to designing a very good heat transfer process. So let us look at some engineering examples of heat transfer. Turbines is one of the workhorses of energy transformation. So in this diagram that we saw, most of the energy that we require comes from chemical energy, and nearly 50% of this chemical energy is transferred to mechanical work using turbines. The remaining 50%, you use it by just heat and convert it into another form, that not directly to mechanical, but to other forms. But more than 50% is used for mechanical work, and that is done by turbines. And all the pressure and kinetic energy, like you have in turbines coming from hydrothermal, hydro uh, uh, energy is through turbines. So turbines are actually the workhorses of all the energy that we get, transforming any of this chemical and potential kinetic energy to work. And most turbines operate at very high temperatures. So which means that you have to have very efficient heat transfer. So what you see here is a turbine blade. Okay, and it's very huge. And it's the turbines are typically of the order of several meters in diameter, and what you see here itself might be about uh, 10 to 20, 30 centimeters each of these things. Now, what we see here is just the outer surface. The inner surface is actually much more intricate. So what you see here, if you just take one of these blades, this is the top view of the blade, and this is the internal cross section along this length, right? So inside the blade, there are a huge network of pipes that are uh, carrying coolant just to keep the temperature of this blade in a controlled manner. So what you see as a turbine blade here, there is of course there is a lot of heat transfer here, but there is also a lot of things that are happening here which you need to control. So turbines, so any small efficiency improvement in turbine to generate work, any small improvement here, because by doing better heat transfer design, is actually going to significantly reduce our consumption of or energy or wastage of reduce the wastage. But let us come to more commonly used products. So this is all some things that we have seen. So this is a CPU fan that is there in any of the computers. This is a sophisticated liquid cooled gaming PC, or this is your mobile phone. And in all these things, you have a microprocessor which is clocking. And the clock speed of this microprocessor is very much dependent on the temperature. So if the temperature increases, the clock speed is going to come down. So it is very important that the temperature of the microprocessor is controlled in an efficient way. So in all these things, a good heat transfer design becomes important. Now, closer to our own body, any animal body requires to maintain the body temperature. So each all living organisms generate heat, and they have to maintain. So by maintenance of heat, what it means is that it has to prevent losses, and most of the losses happen through skin. So what you see here is a cross section of a skin, which is a complicated composite mass. So you have different layers with probably different thermal conductivities. There may be some fluids which are moving and transporting heat and preventing heat from going out. So the complex, this hair, fur in many cases uh, helps to retain heat and so on. So the design of all these things, the natural design that came from evolution, understanding that is also important to understand uh, several diseases. For example, diseases such as hyperthermia, that is excess temperature, or commonly known as fever, or hypothermia, where you have cold fever, or heat stroke that you get in very hot climates. So, all this is related to how the body responds to heat in the environment. So, if you want to understand how to avoid many of these things, you need to be able to understand why the heat transfer failed, or why what happens, what the heat transfer has led to in the blood flow, and therefore to a stroke and so on. Apart from diseases, it's also useful in treatments. Like in physiotherapy, you might have heard this infrared light being used to relieve pain, or in cancer treatment, where you have a heat laser which goes pinpoints to a particular uh, cancer tissue and dissolves them. So, in all these things, you are interacting with heat, with material, and it's important to understand the transfer of heat in these materials as well. Now, coming to our own discipline of chemical engineering, heat transfer plays a very, very important role in many of the processes. What you see here and here is typically what you would have seen in your laboratory experiments in your school. So, this is a laboratory distillation setup, and this is a laboratory reactor where you can carry out reactions by having a stirrer. Now, the macroscopic size of these things in actual industry is really, really huge. So, what you see here as a small heater is what is in the industrial sense, this is called as a distillation column or a tower, and this boiler, or called a reboiler, which actually provides the heat to this column, just as this you have a burner here. This alone is a very huge heat exchanger, which could be several meters in diameter, and maybe about 10 to 20, 30 meters in the length. It's a huge setup. And this could be up to 50, 60, or sometimes even much more than that meters in height. So there is heat transfer not only happening here, there's heat transfer happening in all these uh, plates, what are they known as plates, where there is vapor going up and liquid coming down. And then finally, there is a condenser, again involving heat transfer. So again, efficient operation of all these things and efficient separation of this things that has to be distilled depends on a very good heat transfer design. And for reactors, what you see here is a simple reactor where not much, maybe there is some small heating element here which controls the temperature. But in a reactor, on an industrial scale, you need a reactor which is very well controlled. So you have what is known as jacketed vessels. So in these jackets, there is a thermal jacket where um, uh, uh, there is external fluid that is circulating, or they have a electrical coil that maintains temperature. You have a lot of sensors and so on. So heat transfer that way is very important for chemical engineering industries as well. To summarize, heat or the thermal form is the dominant source of energy for any energy transformations that we have. And which means that if you want to transform energy to some useful work, you have to work with heat, and efficient design of these things uh, to minimize the dissipation or wastage of energy is important. Thank you.